All right, we've talked about all the factors that govern SN2, SN1, E1, E2, mixture. Now we're predicting products. So pause the video, take a minute in your course packet and figure out, we have 4 examples, 2 of them are up here. What would those 4 examples provide as products? If you're just watching me doing it, you're not getting much from it. So this is stuff you should be working on your own before you see the answer. So you've already done that, good job. Water. So what do we do here? We start out by looking at the nucleophile type. Water, that's a weak nucleophile. Weak nucleophiles wait around for a strong electrophile, for something that's very electrophilic. This is a tertiary alkyl halide, so that can very easily form a carbocation. That bromine can leave, that would generate this carbocation here. At this point, once we form a carbocation, if we have a weak nucleophile / base, it's going to do a mixture of SN1 and E1. So SN1, the water is going to add there, it's going to lose a proton. E1, it's going to pull off a proton from the beta position. We have a beta position here, here, and here. There are no protons here, so we can't do an elimination to form a double bond there. We would have to do either side there. And essentially, this, at this point, is a symmetrical molecule, so either side is identical. So the E1 product would look like this, and the SN1 product will look like that. Did I have to indicate stereochemistry for the OH there? No, I didn't. Why not? Again, because this is an achiral molecule. The water, sure, it did add on the top or the bottom, so maybe you added a squiggle there. That squiggle's not necessary. It actually tells me that you don't fully understand what's going on if you put a squiggle. Because if it adds to the front, that's identical in this case to if it adds to the back, because this is an achiral molecule. There's no stereocenter on that molecule. All right, this one's done. What's next? This one here. So what do we got? Start out with the nucleophile. This is a strong nucleophile. Strong nucleophiles don't wait around. It wants to get to that antibonding orbital. This is a moderately hindered antibonding orbital. It's a secondary alkyl halide. That means it's going to do a mixture of SN2 and E2. That's going to provide us with the SN2 product and the E2 product. So that's what we would make in this case. So hopefully you've already done the next 2. If you haven't, do those now, and I'm going to write them up. We have the other 2 examples up. Here we have a strong base / nucleophile that's going to force bimolecular. So this is strong. Here we have a tertiary leaving group. That means it's going to be very hard for a nucleophile to access that antibonding orbital. That means this is going to be E2. What about that? This is a beta position, this is a beta position, this is a beta position. It says to draw all, indicate the major. If we pull off from beta 1 here, indicated this is the beta 1 position, we would form that product. So this is beta 1. This beta 2 is identical to this beta 2. So if we pull off the beta 2 position, we're going to form that molecule there. There's free rotation around that carbon-carbon bond. It's a single bond, so whether or not the double bond's on that side or that side, it's the same product. Which one's the major? This one's the major because it's tri-substituted. The other one is di-substituted. All right, what's going on in this one? This one's probably the most challenging thing you've seen in the video. Well, I would say actually all the stereochemistry stuff is more challenging than this. But this involves the same stereochemistry stuff that we talked about in depth. So what do I mean by that? Well, we have our chlorine leaving group here, and let's go through our standard analysis. We have potassium hydroxide. That's a strong nucleophile / base. We have DMSO that's indicated here. We didn't indicate it here. That's fine. What does the DMSO do? What does a polar aprotic solvent do? It increases the rate of bimolecular reactions whether or not this is in a polar A product or a polar product solvent, it's still going to be the same reaction type. The solvent only really has an impact on the rate. So the strong nucleophile, this was already going to do bimolecular. DMSO increases the rate at which it would do the bimolecular. Okay, so it's a strong nucleophile that's going to force SN2 and E2. So now we have to look at the type of alkyl halide to say, is it going to be SN2 or is it going to be E2 or a mixture? This is a secondary alkyl halide, so it's going to do a mixture. So let's first look at the SN2 option. So this chlorine is a wedge, so for the OH to substitute, it has to add to the back side of that. So the SN2 product is going to have the OH come on the back side of this chlorine, so the new OH bond is going to be dashed like that. The deuterium that's indicated here didn't change anything, so that's still a dashed bond right there. So this would be the SN2 product. What about E2? Again, E2, we look for the beta hydrogens. This is a beta position. This is a beta position. And what is deuterium? What is deuterium? Write it down. Okay, you did it. It's an isotope of hydrogen, so it reacts the exact same as hydrogen. It just has an extra neutron. So essentially, it's a special hydrogen that we can just say, is it still there, is it not still there? It's still there in the substitution product, but if we're doing elimination, is the deuterium anti-periplanar to the chlorine, or is the hydrogen anti-periplanar to the chlorine? This is a really important question, and if you're having a hard time thinking about it here, it's probably a good option for you to look back in the notes. We went through this in depth on, where was it? I want you guys to know where it was. This was unexpected for me to try to do this right now. Oh, here we go. We went through it in depth on around pages 8, 9, and 10 of the course notes. So if you're having a hard time saying this deuterium is going to leave or this hydrogen is going to be taken, which one's going to be taken by the OH minus, go back to that page. Try and think about it. Which one is anti-periplanar to the chlorine leaving group? And what that comes down to, and I'm telling you the answer right now, so make sure you've thought about it before you listen, is that the hydrogen has to be on the back face of the leaving group. So if this chlorine's wedged up, the thing that's behind it is going to be on the other side of this board, so through the board. And what's through the board? The deuterium is through the board. So essentially the OH minus is going to grab the deuterium here. It's just like a hydrogen. Those electrons are going to go down, make a double bond there, chlorine's going to leave. So this is how this E2 elimination is going to work. It can't happen from this location because there are no hydrogens on that location. So the product of the E2 is going to look like that. Note that I did not draw the deuterium in because the deuterium is now gone. If the deuterium was a wedge instead of a dash, it would still be on there. So it's important that you note that you always have to indicate deuteriums if they are on the molecule. But in this case, it is not. So we don't have to indicate it. So that finishes up Chapter 8. We are cooking along. Congrats. We're really getting through organic chemistry now. So make sure you're doing all these predict the products. Make sure you're doing all your homework. The homework's just going to be more and more examples of all of this stuff. So I will talk to you soon.